So you're not likely to do, this is not how you would normally define a relational database, because you'll see, like database is repeated there and operating systems is repeated there. This name is repeated there. Okay, so that's not the way you're likely to do it. And then here's sort of, if you restructured that data along these lines, then we have semesters, and we have this course, that course, that course. We have this student, and in effect, you've preloaded the data with relationships you plan on examining done as you build the table. So now you can ask these questions in those 3 dimensions, but you can't ask questions in any other dimension. So some more advantages. Like I said, you can put a spreadsheet as an interface over one of these, and to get the same effects that you can get with a cube would require complex joins. It's easy to maintain because the data is stored the same way as it's viewed. It becomes very intuitive where you would expect to find data. And then you get much better performance if you're doing certain things. So again, there's no such thing as a free lunch. A cube is built a subset of the data, it doesn't hold all the data. The SQL system is considered the database of record. That's a proper noun that people in the industry use, which just means someplace you need to know what actually happened, and you can't lose that, right? In this day and age, with government regulations and the Securities and Exchange Commissions and the various laws that Congress passed, it's a big deal. You have to keep records of everything that you did, all your transactions for, I don't know what, 7 years or something, right? So typically, you're going to use SQL as the database of record. And if you're actually doing business, like accepting orders or buying, shipping, doing bills, that's going to be out of your database of record, which is the one source of information. Whereas other databases, which are often called data warehouses, whether they be a cube or not, they're copied, the data's copied out of and munged and changed, and it's not the database of record anymore. Maybe a bad example is, no, that's a bad example. A lot of times when I take photographs, I will put one in a file and never touch it. And then I make a copy of it, and I'll start photoshopping and do whatever I want, never fearing that I've screwed it up because I always have that original one there. It's a little bit like that here. And then the cubes will pull out subsets as needed. And it would be very common for a big company to have 6 different departments, like a couple departments in manufacturing, a couple in HR, et cetera. And they might all be running different BI cubes, all pulling data from the same ERP system that has the database of record, but each department wanting to look at data in a different way. And again, the data is generally considered stale. At least it's stale like to the hour level, if not the day or the week level. And then this last point is, if a data set in a table is not multidimensional, meaning there's no relationship between the elements of the records, then it makes absolutely no sense to put it into a cube. Here's an example of this. Suppose we had a SQL table with those, and then we created a 2-dimensional slice. We wind up with there's no overlap in these things. Columns only appears once there, and each of them only appear once, and the first name only appears once. There's no relationships going on between this. All the rest of these fields are empty, so that would have been a bad example. There was no reason to put that into the queue. Okay, let's talk about NoSQL. Some people think that NoSQL stands for no SQL, like SQL's bad. Okay. Other people say it stands for not only SQL. I strongly suspect that the people who invented it meant that, and then to be politically correct, it evolved into that. But this stuff grew up in the really high volume internet companies like Twitter and eBay and places like that. You just could not process the data fast enough. So big data usually means a collection of data sets that are so large or with such a high throughput requirement that you really can't store them. That it would take 10, 100, 1,000 computers just to spread the data out. Okay? And those examples is when you use NoSQL. So a NoSQL database is less functional and has inherently less integrity, but it is much faster. And if you want to know what products are selling the fastest right now in your Target stores, you don't really care whether it was 3,078 or 3,079, right? You do care, was it 100 or was it 3,000? So typically these are used to get really good data, but it's not, quote, perfect data. It's not absolutely correct. So a NoSQL database typically has a simple key value store. So text message, Facebook, real-time cache registers for speed, they'll have a key, and then the data will just be a bunch of fields maybe separated by commas. And then it can just keep writing that and writing that and writing that. So now you're getting this data in, and it's big chunks, completely unnormalized. They don't have fixed table schemas. You can put different things in different rows. And they scale out because they feed the data to multiple machines. And Mongo and Couch are examples of these kinds of open source products. So if you have thousands of Target stores and you're recording every register, let's say there's 10 computers for each target, so 10 times 1,000 stores, you got 10,000 computers that are busily writing records. And they're not even writing them all to like the same database. It's being split across many, many databases. Now you get into the question of, okay, that's wonderful. I got all this data. How can I look at it? I can't run queries against it. Okay? And that's where sort of the innovations came in of this concept called MapReduce, of which Hadoop is by far and away the most common example of it. So what do we got here? We have, the idea is, here's data being recorded. The first record gets a unique key called 1, that's it. And then it's got 3 fields, but they're actually name value pairs. It's actually, record 1 is name John, age 27, state, right? And then the second one, it has city Butte. It's got an extra field. That's okay, you can do that. And then here's the next one. So you could just keep writing these things out. So you wind up with what they call a document model, which is you have a whole bunch of these individual records, and they're not neatly organized into cute little rows, because they don't have to have the same column values. So here's the idea of MapReduce. I want to go through this until you understand it, because it's really an important concept. It's really changed the world. So these are the stages you go through to get real data out of here. Okay? So you're feeding in record, and here's the field: deer, bear, river, car, river, deer, car, bear. Okay. And then the first thing you do is you just take all the records and you just split them. You send them to multiple computers, and that's how you get parallel processing. Okay. So if you got thousands and thousands of these records being written every minute, you can have a couple hundred computers, and one of them's job is a splitter, and it's just pointing them. So now you have 3 computers that are getting a feed. Now, I've only shown one each piece of data, but you have to imagine these are getting feed after feed after feed, right? And then they map it, which means they tear the data apart and they start counting. Say, oh, this record has 1 deer, 1 car, and 1 bear. And this one says, I had 1 car, 1, okay? Now, these guys do what's called shuffling, and they start writing to these intermediate computers. They're writing their intermediate results. He says to this guy who accumulates bears, I got 1, and he got 1. They all had a car, so they all get this guy. 2 of them had a deer, and 2 of them had a river, right? Okay, so now you've got all these computers pulling this data apart, mapping it, and then aggregating it, counting totals. And then you do this step which is called reducing. So this is where map reduce comes in. Now, you ask this guy, how many do you have? I have 2. I have 3. And then you write the final results, and now you say, okay, in that little millisecond of time, we saw 2 bears, 3 cars, 2 deers, 2 rivers. Now again, you have to imagine thousands of these coming in, thousands of these being split apart, thousands of those being shuffled, thousands of those being reduced, and then your result might be 100 different items with totals that are 60, 100, 15, 3, and that's how you can, in real time, you can say, Target can say, what's selling in my store right this minute? And they'll get a feed of all their high volume products with how many have been sold. So this all relies on sort of a phenomena that, I don't know what came first, the chicken or the egg. Map-reduced technologies or cheap computers. You used to do, whenever you wanted to run SQL, you bought a computer, and then you got more customers, so you bought a bigger computer. And then you got really big, your General Motors. They would pay hundreds of millions of dollars for these giant computers. They had like 60, in those days, 64 processors and huge amounts of memory, and they tried to do everything in one machine, okay? And then it just wouldn't fit anymore, right? About that time, because of the PC revolution, it got to the point where you could buy a processor with memory and a computer for like 300 bucks. So they started sticking them in racks and racks and racks. And now you can buy 2,000 computers, way less than you could buy one big computer. So that trend was happening at the same time this technology was being developed. And the other thing that was critical that was being developed, that was part of this, was in order for this to work, all these computers, pretty much all of them, have to be able to all read the same data. And you really couldn't build a big disk subsystem that was big enough to support it. So they come up with distributed file systems. So it turns out each of these computers would have a bunch of disks on them. But no more than a PC. They'd have, let's say, 4 1-terabyte drives on them or something like that. And this guy's job, completely independent of what its processing is to do, is this guy's job is to store all information from, let's say, A to D. And this guy stores all the information from E to J. And anyhow, you distributed the data across all these machines. And when these machines want to read a record, they ask for a record, and the distributed file system underneath knows which computer has that record, and it goes and gets it. Okay, so all 3 of these things happened at the same time. Really cheap commodity computers, a way of map reducing, separating problems, and good, reliable distributed file systems. And Now, I mean, MapReduce is just everywhere. Every big company is running zillions of these now. Here's an example, another one I saw on it. And this is like pulling up census data and then splitting it and then mapping it and then merging and sorting it and then outputting it. So now I think these are like how many people live in each zip code. So this is a bunch of zip code data coming in. Here's a person from here, here's a piece of data, and then you aggregate, and now you can say how many people live in each zip code. And that's a good problem that matches this kind of a model. Okay, so this is an important point too. When you split data across multiple machines to get high data rates and high analysis speed, there's actually a computer science theorem that says it is impossible for a distributed system to simultaneously provide consistency, availability, and partition tolerance guarantees. A distributed system can satisfy any two, but not all three. It says as soon as you take information and split it across two computers, God help you split it across 100, okay? Then because of communication lags and missed messages, you can't be sure that you can ask for your data and get it back and it's going to be exactly correct. Because the one who gives it back might have a stale copy. And so the three pieces are consistency. If you ask the system at any given instant, will you always get the same answer? Well, no, because you might have gotten it from node A, and node A hasn't updated node B yet. So you might get a slightly stale version of the data. Availability is a problem. Well, what if machine A goes down? Half your data's gone. Now you only have data from machine B. And partition is another nasty thing. If they can't talk to each other, this one's updating and this one's updating, and they can't keep each other in sync. So it's a problem. And what designers of this system have done is they said, we're going to make sure we have availability, and we're going to make sure we don't have partitioning, but we're willing to give up consistency. So what they have is instead called eventual consistency. So at any one instant, if you ask for a piece of data, you might get data that's a little bit old, but eventually that data will be updated. So for that reason, you don't use these systems for payroll, because you'd be really mad if you got a paycheck that was the wrong amount. You say, well, it would have been right if you just waited a few minutes before I printed it. And then again, if you're the Walmart manager and you want to know how many spicy Fritos were sold, you don't really care if it's that number. You just want to know about how big it was. You have any question? No, withdraw, okay. So I think that's that. Okay, so that's literally you could spend at least a course, if not 2 courses, on any one of these subjects. You could spend 2 courses on VIQs, 2 courses on MapReduce, 2 courses on programming to SQL, etc. But what we're going to try to do in this course is just to get you aware of all these things. And we're going to write some programs and use some of them so you have a little bit of a gut feel of what they do. And that's what we're going to do. Any questions? Okay, so do try to get that Linux machine up and running in your VirtualBox, and let me know if you have any trouble, because at the next class we'll jump into the first assignment where you'll be using that box for the weekend. Okay, thanks a lot.